Hi, welcome to this webinar. This is a webinar about how GeoticLog deal with coordinate systems for the version 8.1 and over. My name is Anne-Fleur Kinzelman and I will be directing this webinar. But before that, let's say a few words about Geotic. Geotic was created in 2002 by geologists for geologists. These are integrated software to keep the integrity and the traceability of your data, which is quite important in the industry. We recruited a bunch of experts and created different types of software for most of the geologists' needs. In this video, we will be using GeoticLog version 8.1 and we are using the new interface. If you haven't already activated the new interface, you can by clicking on this switch. It will activate the new interface. Prior to version 6.9, coordinate systems were dealt differently. The coordinate systems were actually just local systems. Now you can have real UTM and MTM systems, which are predefined for you, and you could also still use your local grids if you needed to. So if you open a database that was created with a version earlier than 6.9, you will have to migrate the coordinate systems and make them fit to the newest version. Now let's talk about coordinate systems. We cannot emphasize enough the importance of clearly defining the parameters for the definition of coordinate systems. An imprecise definition can easily generate errors of the order of several tens of meters. If you are not comfortable with the definition of coordinate systems, get help from an expert. If you move quickly over this step, you may, after several months of work, find errors that will require you to start over parts of your work. The coordinate system settings are in the Library tab. First, you need to specify the region where your project is located. This is really important, especially if you want to plot your surveys on sections or if you want to convert coordinate systems. This needs to be well defined. For me, I am on North American continent in Quebec, Canada. Depending on the region and the continent selected, you will have a different list of available system types and datum that will be used to define a projected coordinate system later. A quick word about NTV2 correction. NTV2 corrections allows very precise reference conversions between two projected systems. You don't need an NTV2 correction if you are keeping to one projected system. So, if I'm just using UTM, I don't need an NTV2 correction factor. But if I was using UTM and MTM, and I want to be able to get a more precise conversion between them, I will need an NTV2 correction factor. You will have to select the NTV2 National Transformation Version 2 grid file provided by the country concerned. Because of their file size, these files are not included. You must download them. For your convenience, we have included a non-exhaustive list of files available for download. This list may not be completely up to date and may not contain the latest version of one of these files. Now we get to the coordinate system definition. There are 5 types of coordinate systems available. So now let's go to coordinate systems. The first type is the projected systems, UTM, MTM, etc. In GeoticLog, a projected coordinate system follows the meridians, so the azimuth varies according to the latitude of a coordinate. Prior to version 8.1, it was possible, wrongfully so, to define an azimuth for the projected systems, which could cause errors when computing positioning. From this version on, when you have to use a fixed azimuth, you will always have to use a local system. For the common projected system, the azimuth, the combined factor, and the reference point can be set via the word system. We will talk about this type of system in the next section. When creating a new projected system, the first things you need to do is give it a name. So let's create a new coordinate system. And so let's call it UTM. Then you will have to select the type of projected system. So here is UTM. And then select the datum. So we're going to use the 983 datum. If the type selected is a UTM, you will have to specify in which zone it is. So let's say that our project is in zone 18. Then you can specify the numbers of decimal you want and the units. 1, 2, and I would be in metric, in which the coordinate systems are going to be written. Now, let's say a few words about datum. So, what is a datum? A datum defines the parameters to use to convert terrestrial points in Cartesian points. It is a set that might combine a projection and a geodesic system. So datums are approximations trying to fit at their best the non-roundness of Earth. Some are more accurate than others, but also some are more popular. There are several types of datum. NAT 27, the North American datum from 1927, NAT 83, which is the North American datum from 1983. This datum is used by most of GPS today. WGS 84, World Geodesic System from 1984, which is actually one of the most used datum in the world. Not so much in America, but elsewhere in the world, it is very well used. Clark 1980, quite old, but it's still used in Africa, for example. So, as mentioned, none of these datums are exact. They are approximations. That means that you have some shapes that are distorted. That is why people are using different projections, conic, cylindric, on a plan. But using those projections, you can't have all the characteristics right. I mean, the shape, the distance, and surface to be exactly what they are supposed to be. So here is an example, the Panama example. You can see several datums on this map of Panama. They are quite similar, but some seems to be more distorted and they all have different sizes. There is the South America equidistant conic, for which the Panama has a surface of 82,555 square kilometers. The universal transverse Mercator, zone 17 north, with a surface of 75,058 square kilometers, and the South America Albers equal area conic, where the Panama has a size of 75,039 square kilometers, and the geographic NAT 83. At this point here, they seem to overlap well, but look at the ends. It seems impossible to know which one should be the best projection for us, right? So based on the real size of Panama, which is 75,517 square kilometers, The most accurate datum for this country seems to be UTM Zone 17 North and the South America Albers Equal Area Conic. So this is why none of all the data are right. They are approximations, and you have to remind that when you are choosing yours. Now let's go back to GeoticLog. The second type and the most important from version 8.1 is the word system. In previous versions, this system was called the command system, and this command system was set by checking the command checkbox on the desired system. The system, which can't be deleted, is used for calculation from a direction and a deep. For example, for oriented structures, zone thicknesses, channel segments, etc. And by GeoticMine to define the referencing grid. So, in my database, the command system is UTM Zone 18. In older versions, it was possible to select a local system for the command system. This is no longer possible. If it was the case, the command system will be set to the reference system of that local system. This system is the one that needs to be present in all the projects. The system does not need to be visible, but it will always be calculated automatically. Now let's talk about the reference point. The reference point, which was called the definition point for coordinate system in the old versions, is a point that must be near to the center of the projects, of your projects. This point will also be the center of the GeoticMine referencing grid, the center of the drawing. If this point is not correctly set and the surveys are too far from this point, there the survey will be incorrect and you will have precision errors. You have to define it well if you wanted your data to be more accurate. Most of the people are just writing 0 on everything, but this is wrong. The best thing is to choose a point at the center of your project and write its coordinates. By default, the coordinates are from Val-d'Or in Abitibi, Quebec. The azimuth here is the angle between the true north and the UTM grid at the reference point. You have to remember that Geotic works only in true north. You can press the little calculator here to let GeoticLog calculate this value for you. I will let Eric Allary tell you more about what is an azimuth.
Okay, so this is how we calculate this. Okay, so this is just a cone, so that means this is my zone, so it's actually distorted, right? And so this is actually like a zone. Okay, now we have the north hemisphere and the southern hemisphere. So if you're right at the meridian, okay, so there's absolutely no problem. Your UTM, your grid, and your true north grid, I'm always talking about UTM, but actually it could be MTM or other things, right? Will be exactly the same. And that's not a problem. Exactly the same. But if you're here, okay, because of the distortion, the grid north will still be up like this, but the true north is actually like this, because if you're there, the north pole is there, so this is a geographic north, you're pointing this way. So there's a distortion with it too. Okay, so it's the same thing in the northern hemisphere, the southern hemisphere, I mean. So this is the little azimuth that we're calculating into GeoticLog. Okay, basically, the further you are from the central meridian and the further north you are, the angle will increase. Okay, you will have a bigger difference between the true north and the UTM grid.
Well, thank you, Eric. Now let's talk about the combined factor. The combined factor, as its name says, is a combination of different factors such as the conversion, the scale, and the altitude at the reference point. This factor is used to correct the distortion, and it is often given by a land surveyor. You can press this little calculator here to let GeoticLog calculate this value for you. I'm going to let Eric Gallery again tell you more about the scale and the altimetric factors.
When you're here, it's actually larger than the actual distance of your UTM. While when you're here, it's actually smaller. Okay, so you have to compensate for this. Okay, so this is what we call the scale factor. So you have to increase. Okay, so the exact scale is larger. Okay, scale increases in here, and here the scale decreases. Okay, so we have to compensate for this. Okay. If we continue, okay, another way of seeing this, another problem also is that each zones are assumed to be flat. Well, the Earth is actually curved. Okay, so this is my zone. The green line here is my zone, but this is the Earth. Okay, this is exaggerated, but it's just to show you the idea in here. Okay, so you have your Earth ellipsoid. So this is an approximation of the roundness of the Earth. Okay, so this is what the WGS 84 or NAT 83 and so on. Okay, so you have the projection surface in here. So that means that if you're in here, okay, and you measure something, okay, on the field, this is what you measure. But when you get in here, you'll see that your real on the map, it's going to look smaller than what it is on real. Okay, and the opposite is actually true in here, where if you measure something, it's going to appear much larger on your UTM than what it is really. Okay, so that's why we have some formula, and then we can just balance the distortion in there. Okay, so this is also part of the scale factor. Okay. We have, oops, this shouldn't say scale factor. This should say, I wanted to talk about the altimetric factor. Okay, so you have the Earth surface. So you have the Earth surface in black in here. Okay, so this is a real surface. And then in red, you have the ellipsoid, for example, the WGS 84. And then you have your geoid, which is the approximate mean sea level in here, okay, in blue. Okay, so the difference between different things, but the one that you need, you have the ellipsoid height and so on. But if you take the orthometric height, the h in here, and you know your geoid undulation, okay, you can calculate that your little h, the ellipsoid height, is equal to the orthometric height plus the geoid undulation. Okay, and this will be used into the combined factor where to measure the altimetric factor. Okay, so the combined factor that is found in Geotic, okay, this little thing here called combined factor, when you set up your coordinate system, is actually the scale factor multiplied the altimetric factor. Okay.
Now let's talk about a local system. This type of system is also called an orthogonal type system, and it is used to create a planar grid for a sector. You can choose a name, units, and decimals, but also the azimuth. The azimuth here is the angle between the true north and the orientation of your new grid. Again, don't forget that Geotic works only in true north. Then you have to define the definition point. In here, that means that 2000, 1000, 300, in this case of my local grid, correspond in UTM zone 18 to the coordinates 296,100, 5,330,200, and 300. That is exactly how you need to read this. So the definition point for the local grid corresponds to this specific reference point for the selected reference. The fourth type is the geographic systems. Their particularity is that they can be in decimals or in minutes seconds. This type cannot be used to plot surveys on GeoticMine or GeoticGraph. The last type is the archive type. It is a new type that was introduced with version 8.1, which allow you to create coordinate system that will never be calculated by GeoticLog. This type cannot be used to plot surveys in GeoticMine or GeoticGraph. If a local system prior to version 8.1 does not refer to the common system, it is automatically changed to an archive type system to prevent the automatic recalculation of GeoticLog from updating the coordinates. You will then have to manually validate this system and recreate it according to the correct parameters. Now, if you do a modification on one of your coordinate systems, you will have to go to the Utility tab and click on the Coordinates button to recalculate all the coordinates of your project. So once your systems are defined, you will have to go to Project, Edit, and then check the box corresponding to the coordinate systems you want to add to your project. Um, Also, here you have the source system. The source system is the system in which the data is imputed into that project. This is your raw data. The other visible systems will be calculated from this system. Here you can see my visible coordinate systems, and here is my source project in that case. Okay. Before finishing this video, I would like to say a few words about zones. As we saw with the Panama example, we have seen that no projected systems are equal on large surface. That's why, for example, there is in Quebec a specific system called the MTM system. The MTM system, as the UTM system, is also divided by zones, but smaller zones in this case. The system was developed for the whole Canada, but it is mainly used in Quebec and Ontario. People are also using UTM. For example, if your project is in Quebec, depending on where it is located, you should use UTM 17, 18, or 19. Those zones have been created to be more specific and more precise about our data. So there are different things to know about zones. Let's take, for example, UTM, as we were already talking about it. UTM stands for Universal Transverse Mercator, and it is divided into 16 zones. Each zone corresponding to 6 degrees. It goes from the Greenwich meridian, and then it goes from 6 degrees all the time. One zone is 1 million meters wide. Here you have an illustration of the zone 28 of the WGS 84 ellipsoid, but it works the same for UTM. Zones are defined with parallels line, but in reality, because of the spherical aspect of the Earth, it will be larger close from the equator and smaller to the poles. So you will have to see that those zones must be a little distorted to be able to compensate the rotundity of Earth. On that pictures, this is supposed to be 500,000 meters, and this one too. But in reality, this is probably less, so there is some distortion. To go back to the UTM system, another thing you need to know is that the number of each zone is increasing toward east. Now, if we talk about MTM, it is a little bit different. As you can see, you have on the left of a map with the UTM zone in Ontario, and on the right you have the MTM zones in Ontario too. In Ontario, the MTM zones are overlapping in some places, which could be a little tricky if your project is at the border of those overlapping zones. Also, at the opposite of the UTM zones, the number of zones is increasing toward west, and each zone is 3 degrees wide. So those zones are half the size of UTM zones. This size makes them more precise and gives them less distortion. One last thing before ending this video. I just want to warn you that if you are doing an export to a GEMS database, you have to know that GEMS work differently than Geotic about azimuths. When GeoticLog exports into a GEMS database, the azimuth is corrected according to the coordinate system selected to put the projection north vertically instead of the true north. This value can be viewed in GeoticLog next to Azimuth Local label into the Coordinate tab and the Download Survey tab. Note that this azimuth does not correspond to an azimuth measured by a device whose magnetic declination has not been corrected. Also, GeoticLog automatically creates a downhole survey test at the color in the downhole survey table and transform depth for a DDH that do not start at a depth of 0. GEMS require drilling to begin at 0 depth. This therefore affects the wages. If you need to remind yourself some information about coordinate systems, you can click on the Help button and go to Library, Other, and Coordinate Systems. So now it's time for me to say goodbye, hoping that this video will help you to better understand coordinate systems. Bye.